All right, welcome to another video. I want to demo something real quick. I got a comment here. If you open Kindle Cloud Reader, which I believe you can get for free. Yeah, so if you search for Kindle Cloud Reader, the link here is read.amazon.com, and I think you can just download it for free. Um, it's just you need to pay for the books. But what I wanted to demo is this part here, this documents. So you can see I already have three documents uploaded to it. So let's look at this first document. So this is a Chinese Olympic weightlifting document, 344 exercises. So you can see I can go through all the pages. I've got the location marked. I've got the pages. In fact, the location marked, yeah, it works all the same. Now, oh, can I bookmark it? It looks like the bookmark's not here. Well, the bookmark's over here. So yeah, I can do all the bookmarks. I can do all the notes. So I can add a note here. I can copy the information from the book, and then I don't get that annoying um, author's information either. I do get the page number, but yeah. So you can get Cloud Reader for free. To upload these documents, the key thing is you go to File, you go to import a local PDF, and then you find it on your own. I'm not here to encourage or facilitate piracy, anything like that. But you search for the name of the book in Google, and find it on your own, and then select from your downloads. In this case, we can see the example here is this Chinese weightlifting guide, which, to my knowledge, was available online for free. So you select that, then you click open, and I already did that, so it'll show up here. And now, if you want to access it, all you have to do is go to Documents instead of Books, and you can do the same bookmarks. Everything will be the same like that. So I just wanted to start this video off um, demoing that because that was brought up in the comments. But now I'm going to move on. These are all paid books, so in order to get things to show up here, you do have to pay for the books. They're expensive, so I do recommend, especially for things like a PDF you find online, not necessarily something copyrighted. Go ahead and go to document, do your Google Foo, download it to your local files, then go to File, go to Import a local PDF, and then it'll show up in Documents after you've downloaded Kindle Cloud Reader, which you can get by Googling for Kindle Cloud Reader and then installing that. And you know what? Let's do Charles Dickinson or Charles Dickens PDF just to really demo that. So now we can see we've got Project Gutenberg here, which is all open source public domain books. So we can click on A Christmas Carol by Charles Dickens. And look, for this one, they even have a Kindle version of it. So we can even, if we find the Kindle version, we can go with that. So let's click that. Okay, so now we're going to, I'm going to name it Christmas Carol. Under my downloads. All right, and then I'll go to here and do import. Oh, and you know what? It's not a PDF. So if there is an option for a PDF, that's probably the better option. So Now here's a send to so PDF is probably the best way to go. The Kindle, I can try that in my downloads. So if I go to downloads, yeah. So if I just double click here, there. Now since it's a Kindle document, it shows up here as a Kindle document. If I go to my library and go to my books, now it shows up as a book. That's a local file. So there's all kinds of formats. If it's a PDF, go ahead and import it as a PDF. If it's any kind of Kindle file, as we see, there are multiple. There's send to Kindle. These are all Kindle files. Just double click it and Kindle will open it automatically. All right, so I don't need that in here, so I will delete it permanently. And then I'll move here and we'll continue with the series. So I need to show my notebook and go to this last one. Let's read the key takeaway again from the last video. So the key takeaway from the last video was any concept in machine learning needs to be expressed in numbers or quantities. When we talk about similarity, we need to translate it into formulas that can express such a quantification. And last video was pretty heavy. We went through, well, let's see what we went through in the last video. So last video, what we did is we reviewed ways to measure distance between different observations and evaluate which ones are closer. So there are various ways to do that, various types of distance used in the context of machine learning algorithms. The first type of distance we reviewed was Euclidean distance, the traditional and most well-known method for calculating distance. The second and there's a mathematical equation associated with that. This is the equation here. The next one we reviewed was Manhattan distance. This is if you could not go directly in a straight line from one place to another, and you had an obstacle, for example, a skyscraper in Manhattan, and you had to go around the block. This would be the distance there. So we have a equation for that as well. We can see we can't unlike the Euclidean distance where we can just go from one point to the other directly from S1 to S2. We use the Manhattan instance instead, where we have to go to one point and then another point, or possibly even a series of points to get there, but we can't go directly from one to the other. So there's a mathematical formula for that as well, we see here. And then the final way, common way of measuring distance that was brought up in this book is the cosine distance, also known as the cosine similarity. And I'll be right back. I need to take a quick break. All right, so I am back. So the last one was the cosine difference. In this case, we're dealing with an angle. So if we look at the graph for that, we can see it's more, we've got this curving line here. So we're not interested in this case in the distance between the 2 points. We're interested in the angle between the 2 points. And to be clear, I actually did use incorrect language there. It's not that we're interested in the angle between the 2 points. It's that we're interested in the angle between the 2 vectors that arrive upon the points. And where the vectors start is what determines that distance. And they'll start in a converged at one point, and then they'll converge, they'll branch off from one another, and that angle of the branching is what we care to measure when we use the cosine similarity, also known as the cosine distance formula. And we can see the formula is right there. It's just 1 minus the cosine of this angle. And then there were other types of distances commonly used in AI, Minkowski distance, Hamming distance for text. and even others. And then who knows, if you're an enterprising person, there might be opportunities to discover different kinds of distances possibly. So exciting things to be learned about. The other thing that would be pretty cool is instead of having to discover your own kind of distance, just learn about out there bizarre ways of measuring distance. So let's go to ChatGPT. So I learned about a few different ways of measuring distance. The first way of measuring distance I learned about is the cosine distance. The second way is the Manhattan distance. The third way is the Euclidean distance. In addition to that, I learned of Minkowski distance and Hamming distance. Now tell me some more lesser known and lesser used ways of measuring distance. Okay, so in the area of ChatGPT, you get the whole view. You don't see just what's in the textbook. So you can learn about Jaccardиan distance and see if you can apply that to AI. You can learn about dice distance, see if you can apply that. You can learn about this one. So you can see how powerful this is. Before, your availability of what knowledge you known about would be very limited. You'd have to learn it from a professor. You'd have to learn it from a textbook. But now, we can see you can learn it just by asking ChatGPT. You can have loaded up into your mind all new things. So like in statistics, this distance is a quantity which represents a notion of similarity between two probability distributions. So how can you apply that to what you're doing? Is that a better way of measuring distance in this case? So you can see it's we're in a whole new world, that would have been impossible before ChatGPT. I mean, I guess you could have Googled how many different kinds of ways are, and already you can see it was not as good of a user experience. So ChatGPT is a game changer. Okay, so I will not describe all the different methods, but we'll focus on two that are more practical for many scenarios. So he's not going to describe all the different methods for what? Oh, I think these are the methods to rescale the data, because I think a decent example is like we want to know. Yeah. So a good example is like if this ray were way out to here and this were to there, and we wanted to know and all so let's use this as an example. Let's say that the grid in Manhattan, each block is 1 by 1. So this would be a 1, this would be a 1. So you'd have to go a Manhattan distance of 2. So let's say that to come up with that Manhattan distance for how to get from one side of the block to the other, even if the only data point you had was 10 blocks over on this way, since we know that they are all 1 by 1, we can shrink that down. We can scale it and just focus about this to plug into our Manhattan distance formula, because we're not trying to measure from the 10th block over to the next, we're just trying to measure from one block to the next. So if the value we get, the input we get for our equation is 10, because it came from 10 blocks over, and we can make that assumption fairly that each is just 1. Now we can do a rescaling on the value to make it more comparable to that other side of the block. Okay, so the author will not describe all different methods of rescaling, but we'll focus on the 2 that are more practical for many scenarios. So the first method of rescaling is normalization, aka min-max scaling. This linear transformation of the data results in a change of scale of the existing variables. The goal is to bring them to a similar scale. Typically, the destination scale will be bracket 0, comma 1, or bracket -1, comma 1. One typical formula to apply this transformation is the following. So this is the formula for normalization. And we can see it's x, the scaled, because what you're trying to do is as we mentioned, we're trying to rescale the values. So the rescaled values are equal to the original value minus the minimum value, that product divided by, or sorry, that, yeah, or no, that, what is it called for subtraction? So sum product quotient, SUM product quotient. What is the name of that for subtraction? I think it's difference. Difference. Oh. Difference. Yeah, difference. So the difference between x, between the value you have and the minimum value, divided by the difference between the maximum value and the minimum value, the quotient of that is equal to the normalized value. So where x min and x max are the minimum and maximum values respectively for the variable x. This normalization process is done independently for each of the dimensions of the vector. Standardization, aka z-score normalization. The goal of this transformation is to center the distribution of the variable around a 0 mean and a standard deviation of 1. So x scaled are re-scaled values. In this case, equals the difference of your data point x minus the mean. So mean, median, mode. Remember that. So the mean would be the average. So minus the average divided by the standard deviation. So the quotient of that is your scaled value. Where x mean is the mean of variable x, and x std is the standard deviation. The resulting variable is therefore centered around 0 and has a standard deviation of 1. It is usually applied to variables with a Gaussian distribution and will result in a normal shape. However, it can also be applied to other distribution shapes. This type of transformation is essential when we use neural networks because neural networks tend to prefer small input values slightly above or below 0. Large numbers as input do not work well with neural networks. At this point, we have seen that we should transform our input data and rescale it so that when we compute distances, we get adequate results. Now it is time for clustering finally. there are many different clustering algorithms. They primarily differ in how they iteratively approach the cluster formation, centroid based. Starting with the assumption that there are k clusters, k centroids are randomly chosen initially. The algorithm will iteratively find the observations closer to the centroids, recompute the centroids, and find the new observations closer, and so on. K-means is an example of this type and is probably one of the most popular algorithms. Those algorithms work well when there is a confident expectation that clusters will have a sort of circular shape around such centroids. But sometimes clusters may show different behaviors, still very popular and straightforward to understand and implement. So now we've got a number of ports used, number of VLANs used, and we've got the clusters are now colored. And then we've got, it looks like vectors maybe? I'm not sure what these dotted lines are. The distance between the observations and the centroids will determine the cluster they are assigned to. In the case above, we have k-means with k equals 3, so the centroids have resulted in a good spot. And we get the 3 clusters that apparently exist. However, what if the data was not so easily observable n dimensions, or we simply do not know how many clusters there are? In the above example, if we use k equals 2, we would get something like the below. Oh, okay. Oh, I see. So like the connecting the dots across 3 groups, since there are 3 very nicely clustered groups, is pretty easy to do. But if we need to connect the dots across only 2 groups, we need to make a decision which of these quantify the lone group and which of them are the 2 groups expressed as a single group. So the algorithm will always find as many clusters as we instructed. So here they picked these 2 groups here to be in the same cluster, and this one to be the third cluster. And now the kind of distance between the 2 is from a new point and not a point within each cluster. Whether they really make sense or not is subject to interpretation. In this example, as we intended to find 2 of them, both centroids are positioned in mathematically sound locations to satisfy such a requirement. So, how can we know in advance the correct number of clusters? You may have other sources of information or prior knowledge that indicates what that number could be. Otherwise, the only option is trial and error. Nevertheless, still, how do we know which one? There are various methods. I will only describe the elbow method. You know what? This is a good stopping point. So that's the end of this video. Just a short video today. When I come back, the next video will be on the elbow method. So thanks for watching and see you in the next video.